Hello and welcome. Now we have reached to the final stage of this chapter. In the final part, we'll be studying about atomic number and mass number. Now that we have learned all the components of atoms, electron, proton, neutron, let's learn about what is atomic number and what is mass number of an atom. Atomic number is defined as the total number of protons present in the nucleus of an atom. To refer a previous question, if you may remember, I had given you a glimpse of what an atomic number is. The number of protons in an atom is known as the atomic number, and it is represented by the letter Z. All atoms of an element have the same atomic number. Okay, so all atoms of an element, for example, carbon, for example, of oxygen. So all the atoms of this element, all the atoms of this element, both of them. Okay, so all the atoms of the elements of carbon would have the same atomic number, and all the atoms of the element of oxygen would have the same atomic number. So in fact, elements are defined by the number of protons they possess. For example, hydrogen, the atomic number of hydrogen is 1. So the Z for hydrogen is 1, because in hydrogen atom only one proton is present in the nucleus. Similarly, for carbon, the atomic number is 6. Okay, so the number of protons is equal to number of electrons. This we know. So if we know the atomic number of an element, we can conclude the number of electrons from it, since the number of proton is equal to the number of electrons in an atom. Mass number. The mass number is defined as the sum total of the number of protons and neutrons present in the nucleus of an atom. This also, if you may remember, we had seen in one of the previous slides, in one of the previous sections of this chapter, was that the total mass of an atom is determined by the mass of its proton and mass of its proton and mass of its neutron. Why so? Because the electron, we know, is almost negligible in mass. So we do not count the mass of electron. Rather, we look at the mass of proton and we look at the mass of neutron. So these two elements, which also form the nucleus of an atom, the sum total of the number of protons and neutrons present in the nucleus of an atom will be the mass number. Why the sum total of the number present in why the sum total of the how many protons and how many neutrons? Why number is important here? Number is important here because, as we had read earlier, that one proton could be designated to be equal to 1 U. Okay, so when we know that one proton is equal to 1 U, we can easily and very safely say that 8 protons is equal to 8 U. And since the mass of proton is nearly equal to the mass of neutron, since the mass of proton is nearly equal to the mass of neutron, we may also say that if there are 8 neutrons, all right, so that 8 neutrons, the mass of those 8 neutrons would also be 8U. So that is why, if we know only the total number of protons and neutrons present in the nucleus of an atom, we may determine the mass number by adding them all together. And like Z represented the atomic number, mass number is represented by the alphabet A. Protons and neutrons are also called nucleons. Okay. For example, mass of carbon is 12U because it has 6 protons and it has 6 neutrons. Okay. 1 proton, 1 U, 1 neutron, 1 U. So 6 protons, 6 U, 6 neutrons, 6 U. So the total mass is 12 U. Similarly, the mass of aluminium is 27 U, because over here there are 13 protons and there are 14 neutrons. So 13 protons, 13 U, and 14 protons, 14 U. When you add them together, you get the mass number of aluminium, that is 27 U. Notation of an atom. So in the notation of an atom, the atomic number, mass number, and symbol of the element is to be written. For example, if X over here is an atom, okay, on the left hand side of this atom, towards the bottom, we write Z, that is our atomic number, and just towards the opposite side, on the upper left hand side, we write the mass number that we designate by A. For example, nitrogen, the atomic number of nitrogen is 7, so we write 7 here at the bottom hand side of the left of the alphabet N, and towards the upper side we write 14, that is our mass number. That is how the notation of an atom is done. Question: if number of electrons in an atom is 8 and the number of protons is also 8, then what is the atomic number of the atom? So we know that the atomic number of the atom, that we also designate it by Z, the atomic number of the atom is equal to the number of protons. And since the number of protons is easily given to us over here in the question, we can safely say that the atomic number of this atom is 8. What is the charge on the atom? Now here in the question, it is explicitly mentioned that the number of electrons is 8 and the number of protons is also 8. So since the number of electrons is equal to the number of protons, that means the atom is in a stable state. It does not have an excess of charge or any deficiency of charge. So charge in the atom, we can safely say that there is zero charge on the atom. The atom is in a stable state. What is the mass number of oxygen and sulfur atom? The mass number of oxygen atom, it is 16, and the mass number of sulfur atom, it is 32. Okay, so mass number is defined by the number of electrons, the number of protons plus the number of neutrons. So number of protons and neutrons in oxygen atom is 16, that is the mass number, and the mass number in the sulfur atom, that is the number of protons and neutrons in the sulfur atom, is 32. Now we will be learning about isotopes. Isotopes are defined as the atoms of the same element. Okay, same element here is important to remember, having the same atomic number but different mass numbers. So this means that since we are talking about the same element, the atomic number is same. That means the number of protons in this particular element that we are talking about would always be the same. But since there is a difference in the mass number, that means, and since we know that mass number is equal to number of protons plus number of neutrons, so the number of neutrons, this must be fluctuating. Okay, so I'm repeating this again. Since the number of protons plus number of neutrons is equal to the mass number, and in isotopes over here we have different mass numbers, so we can safely say that since we are talking about the same element and the number of protons is same, there must be a difference in the number of neutrons of that particular element. So there are three isotopes of hydrogen atom. One is protium, which we simply designate by the letter H. One is the deuterium, which we designate by the letter H or D. Most commonly we take D to avoid any confusion from the other isotope of hydrogen, and same goes for tritium, we take the alphabet T. So the atomic number would be the same in all of these. That means one here, and one here. That means number of protons in protium, in deuterium and tritium is equal, that is 1. But there is a difference in neutrons, alright. So in protium, we observe that there are no neutrons. Remember that question in one of the previous slides where we had that, mentioned that element which has no neutrons in it. That is this isotope of hydrogen, protium. It has no neutrons. This isotope of hydrogen only has one proton and one electron. In the deuterium, the other isotope, we have one atomic number, that is number of proton is 1 and the mass number is 2. That means this isotope of hydrogen has one neutron and one proton. And in the third one, the mass number is 3. That means in this particular isotope, we have one proton, okay, since the atomic number is 1, but the number of neutron over here is 2. So protium has 0 neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. The atomic number of each is 1, but the mass number is 1, 2 and 3 respectively. And the chemical properties of isotopes are similar, but their physical properties are different. Now since their protons, the number of protons and the number of electrons is same in all the isotopes, so we can safely say that the chemical properties are similar. That means the way this particular element behaves is same, okay, but there has to be some difference in some of its qualities. Since there is a difference in the number of neutrons, so there is a difference in the physical properties of these elements, protium, deuterium and tritium, as you can see over here. So the physical properties are different, but the chemical properties are the same. Let's talk about the average atomic mass. Chlorine is a peculiar case because chlorine occurs in nature in two isotopic forms. One has the mass number of 35U and one has the mass number of 37U. So if we take a few, say, atoms of chlorine, okay, these two isotopes would always be in the ratio of 3:1. So three, suppose we have taken few atoms, so three, some parts, three would have the atomic number, sorry, mass number as 35U, and the other part would have 37U. So if we go on like this, we cannot, obtain our very, a chemical sort of stability from chlorine, all right. Chemical sort of stability in the sense that if we are to process and, try to conclude some important chlorine reactions, we have to consider one mass number so that we may observe what sort of changes there are taking place. Okay, so for the safety of that, we have obtained one average atomic mass of chlorine, that is 35.5 U. Okay, this does not mean that one atom of chlorine has this much mass number. This only means that if you take a certain amount of chlorine, it will contain both the isotopes of mass number having 35U and 37U. So for our safety, for our convenience, for our understanding of how chlorine functions, we are taking the average atomic mass as 35.5 U. Applications of isotopes. Some isotopes have special properties which find them useful in various fields, and some of them are the isotopes of uranium. This is very useful and is used as a fuel in nuclear reactors. You may have heard of some fusion reactions and you may have heard of some fission reactions as well. So these are nuclear reactions, okay, and to propel these sort of reactions, a very small amount of isotope of uranium is required. So a small amount of isotope of uranium can, result in the production of huge amounts of energy, and with that energy there is either fusion, that means, two atoms come together to form something, okay, and energy is radiated, or either there is fission, that is, an atom is divided into some particles. All right, so fusion and fission, the two nuclear reactions, this is made by, usually done by the isotope of uranium. Isotope of cobalt is used in the treatment of cancer. So there is a medicinal purpose of cobalt. It is used in the treatment of cancer, and the isotope of iodine is used in the treatment of goiter. So there are two medical uses over here. That isotope of cobalt is used in the treatment of cancer. You may remember is that C, like C stands for cobalt and C stands for cancer. Okay, and iodine, isotope of iodine is used in the treatment of goiter. You may remember this by a very functional use of iodine is that iodine is found in salt, and when you have that deficiency in some level of iodine, that means if your salt, there is some, disturbance of balance in your consumption of salt, then you have a goiter problem. Okay, so the isotope of iodine is used in the treatment of goiter. All right, this small diagram over here is a very simple function of how a nuclear reaction takes place. We have control rods, we have coolants, we have the nuclear fuel, we have some moderators, we have radiation protection barrier, and we have also some hot coolant as well. That that is basically the exit line of this cold coolant. Okay, so this looks simple here, but we will definitely be learning about this later. Isobars. We've learned about isotopes, but what about isobars? Isobars are atoms of different elements. Isotopes were of the similar elements. Isobars are atoms of different elements with different atomic numbers. Since they are different elements, so the atomic numbers would be different. Okay, so different elements with different atomic numbers which have the same mass number, they are known as isobars. So there is no definite over here that the proton number is same or the neutron number is same. No, we are talking about the mass number as a whole. So there is no equation between the number of protons or between the number of neutrons. We are simply talking that isobars are those atoms of different elements. They must be performing different properties altogether, be it chemical, be it physical, because they are different elements and they have different atomic numbers, but they have the same mass number. So coincidentally, the number of protons and neutrons are different, but the sum of those protons and neutrons, they coincidentally occur to be the same. For example, calcium, the atomic number of calcium is 20 and the atomic number of argon is 18. But both of them, they have the same mass number, that is 40. So for both calcium and for both argon, we have the same mass number, that is 40, despite both of them being different elements and despite both of them having different atomic numbers. Yes, in this small diagram over here, there is another example of isobars. I stands for iodine over here, and Ze, it stands for xenon. So you may observe here that the atomic number is different. There are 53 protons in iodine, and there are 54 protons in 54 protons in xenon, and the number of neutrons is also different. There are 78 neutrons in iodine, and there are 77 neutrons in xenon. But coincidentally, the sum of the protons and neutrons of both iodine and xenon, the mass number, that is, it happens to be the same, that is 131. So iodine and xenon are isobars. Question 1. For the symbol H, D and T, tabulate the 3 subatomic particles found in each of them. Symbol H could be simply taken as our protium, that is our isotope of hydrogen. Okay, so the 3 subatomic particles would be isotope. We know it has, so let's divide it. Okay, P, positive P stands for your proton, this is your electron, this is your neutron. So protium, we know the atomic number is 1 because the element is same, right? So we'll have 1 proton, we'll have 1 neutron, but this isotope of hydrogen, it has 0 neutron. For the second category, that is the deuterium, the other isotope of hydrogen, it also has 1 proton number because the atomic number is the same, because all of these, they are basically the same element. Number of electron will also be the same, but there is 1 neutron in deuterium. And for the last one, for the tritium, again, since we are talking about the same element over here, so same number of protons, same number of electrons, but tritium has 2 neutrons. Okay, so we write 1 1 in protium, we write 1 2 in deuterium, and we write 1 3 in tritium. So these are the subatomic particles found in protium, deuterium, and tritium. Next question is, write the electronic configuration of any one pair of isotopes and isobars. So electronic configuration of isotopes we have just seen over here. Protium, deuterium, tritium, these are basically isotopes, right? So these are your electronic configuration of your isotopes, all right? But what about isobars? So we saw in one of the previous slides that calcium and argon, they have the atomic number as 40, although their mass number is 40, although their atomic numbers, it varies. So calcium and argon, they have the same mass number, although their atomic number is different. So these are isobars. Okay, these are examples of isobars. Whereas in the previous slide where I told you about protium, deuterium, and tritium, those were the example of isotopes. So with this, we come to the conclusion of this chapter. That was the structure of an atom. Let's have a quick revision and let's see what we learned in this chapter. Very quickly, credit for the discovery of electron and proton goes to electron J.J. Thomson, Goldstein for proton, and for neutron we have Chadwick. J.J. Thomson proposed that electrons are embedded in a positive sphere, the Christmas pudding sample. Okay, Rutherford's alpha particle scattering experiment led to the discovery of the atomic nucleus, where he made those alpha beams, bombard with a thin gold foil. Okay, with this experiment, he led that there is some positive charged atomic nucleus. Rutherford's model of the atom proposed that a very tiny nucleus is present inside the atom and electrons revolve around this nucleus, because some particles, if you may remember, they directly had rebounded, and since the helium ions were positively charged, so with that he concluded that there must be some atoms, and those atoms must have some concentration of positive charge at the center, at the nucleus. That is why they deflected, they directly rebounded. Okay, and with that he safely assumed that most of the alpha particles, since they were able to pass straight through, so he concluded that electrons, they revolve around the nucleus. Niels Bohr's model of the atom was the most successful one, because he gave the concept of discrete orbits. If the atomic shells are complete, then the atom will be stable and less reactive. Like we see in the inert gases, they have they have that stability of 2 electrons in the outermost shell or 8 electrons in the outermost shell. Three subatomic particles of an atom are electrons, protons, and neutrons, where the protons and neutrons, they are the nucleons of an atom, because they basically make up the nucleus of an atom. Electrons are negatively charged, protons are positively charged, and neutrons, they have no charge. They are simply designated by the letter small n. Mass of an electron is about mass of an electron is about 1 by 2000 times the mass of an hydrogen atom. The mass of a proton and neutron is taken as 1 unit each. So mass of an electron, we can safely say that it is negligible, whereas mass of a proton is nearly equal to the mass of neutron, and both of them can be taken as 1 unit each. Shells of an atom, that is the energy level, they are taken as K, L, M, N, where they are also designated by energy index as 1, 2, 3, 4, corresponding to this K, L, M, and N. And finally, the atomic number of an element is the same as the number of protons in the nucleus of its atom, which can be designated by the letter Z, and the number of protons is equal to the number of electrons. The mass number of an atom is equal to the number of nucleons in its nucleus. That is, mass number A is equal to the number of protons plus the number of neutrons. Isotopes are atoms of the same element. Remember it, same element, which have different mass numbers. Since they are the same element, so their atomic number would be the same, but their mass number would be different because of the different number of neutrons present. Isobars are atoms of different elements. They coincidentally have the same mass number but different atomic numbers. Different atomic numbers because they are of different. And elements are defined by the number of protons they possess. Okay, why? Because we can simply say that atomic number that is represented by Z is the number of protons that element has. So elements are defined by the number of protons they possess. So with these points, we come to the conclusion of this chapter. We'll be learning more about atoms and molecules and matter and everything later on. Thank you so much for bearing with me today. I hope that this chapter is clear to you, and I hope that all these points in conclusion, they make up this chapter very more cohesive towards you. So thank you so much, and take care and study well.